I'm going to talk to you now about the motor effect. This is the effect that a current-carrying wire experiences when it's in another magnetic field. So, if we have a wire with a current going through it, it will have a magnetic field around it. The magnetic field will be circular, and we can find the direction of that using the right-hand grip rule. You point your thumb along the direction of the current, and your fingers curve to show the direction that this is going in. If I show you an end-on view, we might be able to see this slightly better. So at A, looking down the wire, there is a circular magnetic field, and the direction here is clockwise. If we look at the other end B, here is our wire. We're looking down the wire. The current is coming towards us. We have a circular magnetic field, and this time the magnetic field direction is anti-clockwise. Now, if we put that wire in a permanent magnetic field, it feels a force or experiences a force. Let's draw our magnet. North and south. Here's our wire. We'll make the wire blue, and we'll say that the current is going away from us. What we end up with is the following. Our magnetic field around the wire ends up looking like this. And as we showed up here, the magnetic field is going in this direction. And our magnetic field for the bar magnets, for the permanent magnets, ends up looking like this. This, of course, goes from north to south. Because all of the magnetic field lines bunch up above the wire, we end up with a force being experienced downwards. Now, there are a few ways that we can change what happens to that wire. If we want to change the direction, we can swap the poles around. So this would become north, this would become south, and the wire would go in the other direction. Or we could swap the current direction. So instead of going into the page, it would come out of the page. If we wanted to increase the force, we could use a stronger magnet or use a larger current. Both of those will increase the force. Now, the direction that this goes in can be found using Fleming's left-hand rule. With your left hand, the first finger points in the direction of the magnetic field, the permanent magnetic field. Your second finger points in the direction of the current, which in this case is into the page, and your thumb shows the direction that the wire is going to move in, which is downwards. Now, if we had two wires, or a coil of wire, in a magnetic field, so this time we're going to use a coil, and we're going to have our permanent magnets there. Here is one side of our coil. Here is the other side of our coil. Current's going in there, round the back, and out here. This side goes down. This side goes up. If this was actually pivoting, if we add a pivot here, something that this is going to turn around, then instead of just straight up and straight down, we get circular motion. So this starts turning in this direction, and this in this direction. Now, as it currently is, when the coil reaches the vertical position, so when it gets to here, it will stop moving. There'll be no force on the wire. You probably saw this when you made the motors. They sort of vibrated when it was in the vertical position, trying to move a little bit but not being able to. To be able to complete the rotation, we need a device called a split ring commutator. That's better. Split ring commutator. This allows the current direction to change every 180 degrees. Now, I'm going to show you on this motor here. This bit here is our commutator, this copper-coloured cylinder here. And if I turn that very slightly, can you see that little black line that goes down the centre of that cylinder? That is our split in our split ring commutator. If I turn this a little bit more, there's another split in our split ring commutator. These brushes, these little wires here, are resting up against the commutator. They allow the current to transfer from our inputs into the wires and allow a force to be felt by the motor as it turns in the magnetic field. If we have a look at the model, which is like the one that you made in class, we have a slightly different setup. We have our wire just here, which goes down the side of our spindle, the axis that it's going to rotate on. And these here are our brushes. These two wires coming in here, resting up against that. So every time it gets here, its momentum allows it to move on a little bit further, and then it makes contact again, which allows the force to be felt in the wire and allows it to keep turning. Again, the direction that the coil is going to turn can be found using Fleming's left-hand rule. Again, first finger field, second finger current, thumb motion. So this wire is going to go upwards. If the current is going into the page on this one's going to go downwards.